Alrighty, here we're going to talk about gas mixtures. So this is combinations of gases that are mixed together. They'll behave mostly the same way as we're doing stuff. They're going to be a little bit extra, and we're just going to take care of that. Okay. Um, let's see how we're gonna do this. Okay, maybe move on. Okay, so gas mixtures. I wouldn't say law here. I just didn't edit this out apparently. So gas mixtures. Our rule here is if the gases are behaving independently with, then they do not, if the gases do not react with each other, then the gases are behaving independently, which means that PV equals nRT is going to work for all of the gases in the mixture. Okay. This, uh, and a consequence of this is going to be Dalton's law of partial pressure. So we're going to kind of look at that as we do it. Okay. Because we're in a mix, volume R, of course, and temperature are going to be the same for all gases. Okay. Which means that uh, we're going to have for each gas, I don't know why I'm drawing a blank on why each is spelled weird. That's what my brain is frozen on right now. For each gas, we're going to label these as I. For each gas I, the pressure of that gas is equal to the moles of that gas times R times T over V. This is just solving the ideal gas law for pressure, okay? What Dalton's law of partial pressures tells us, let me do this a little bit differently. We'll do this in green. Dalton's law of partial pressures is telling us that the total pressure, right, of all the gases in the mix together is equal to the sum of the pressure of each gas. Okay. What we're seeing here then is this concept of a partial pressure. So a PI is a partial pressure, which is just the pressure of the one gas in the mixture of gases. This is the pressure of a gas in a mix of gases. Okay. Dalton's law tells us that the total pressure of the mix is the sum of adding all of the pressures together. So what that means is that P total is equal to, if you have three gases in your mix, the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. Right? You can have as many gases in the mix as you want, but the individual pressure of each one of those is going to add together to give you the total pressure of the gases in your mixture. Okay. It's a little, it's kind of straightforward, and hopefully it makes sense. And we can talk about this more if we need to. Okay. Total gases in the mix. Okay, so we got partial pressure. Another thing that we can get here is something called mole fraction. Mole fraction is this unit. It's kind of like concentration. We get into Gen Chem 2, we talk about it in terms of concentration. But for gases and such, we'll use, it's kind of this fancy curvy X thing, or a cursive X. Maybe it's a chi, the Greek letter chi, if you want. The mole fraction of gas I in a mixture is the moles of gas I divided by the moles total. Okay. It's kind of like you could do mole percent by doing mole fraction times 100 to get the percent. Okay. Mole fraction is one of those things that has no units, because essentially we're taking moles and dividing it by moles. So there's not going to be a unit with that because they've all canceled out. So there's no unit. All of our mole fractions should be less than 1 because it's a fraction, it's a portion of a whole. And our total should be equal to 1, right? The total mole fraction should be 1. Because if you take, say you have a mixture that's 50-50 of two different things, the mole fraction will be a half for each one. You add the two halves together, that's a whole. So your mole fraction total is always equal to 1. Okay. Now, because PV equals nRT, remember that, PV equals nRT. Come back, man. There we go. Because PV equals nRT, we can solve an expression for mole fraction and say this is equal to the partial pressure of a, keep clicking stuff, partial pressure in a gas in a mix divided by the total. Okay. This gives us a link between mole fraction and pressure so that we can kind of figure out some stuff. Okay. And so these might be helpful things. Okay. Let's look at an example, and then when we talk about stuff in other videos coming up, we will use Dalton's law of partial pressures to help us solve some stuff. Okay. So let's tackle this thing. All right. Let's see. What are we doing? We're going to remember that PV equals nRT as we go. Okay. What do we have here? We have a 10-liter cylinder. It's filled with nitrogen and nitrogen monoxide at 25 degrees C and 14.75 atmospheres. And we know this thing contains 6.022 moles of nitrogen. Okay. We want to know, what is the mole fraction of NO in this mixture? Okay. Mole fraction of NO is what we're looking for. And we call this chi NO. Okay. So ultimately, this means we need to know moles of NO divided by moles total, okay, to get that done. All right. So this is going to take us 3 things to do this. We got to figure out what the total moles are. Okay. That is step number 1. Okay. So we got to find the total moles. Okay. Keep in mind, these things that we were given are total things, right? The temperature and the volume are for the entire container. The pressure here we were given, we were told was for N2 and NO. So this is the total pressure. Okay, if we use the total pressure and the other data we have, we will get total moles. And we can get this by solving for N. Again, this is going to be PV over RT. Okay, the total pressure we have is 14.75 atmospheres. The volume we have is 10.0 liters. This is going to be divided by R. Since we have atmospheres, what we're going to use is 0.082058 units of liter atmospheres over kelvins times moles. This you can look up on the info sheet, the list of R's, you'll have that, so you don't have to worry about it. Temperature. Oh shit, no one yelled at me, probably because I'm doing a video and not a class. We need to convert our 25 degrees C into Kelvin. So our temperature, 25 Celsius plus 273.15. You know, I really need to stop leaning my hand on things as I'm doing this. Okay, let me go back. Okay, this should all be here. Good. Okay, 273.15. Of course, it's switching back to red, which I'm not a fan of. Okay, so this is 298.15 Kelvin. That doesn't look like a K. This is a K. All right. This we're going to plug into our equation here and say 298.15 Kelvin. Okay. We're going to multiply the top. We should get 147.5. Multiply the bottom, and we get 24.4656. This weird fraction has units of moles. And if we solve this, This is 6.02887 moles. This is total, if we want to remember that. This should have 3 significant figures because of 10.0 liters. All right, so that would be here. Okay. All right, next step. 2. We don't need just total moles, we need moles of NO. Okay, now the nice thing is here, I mean, you could come at this several ways if we wanted to. We don't have partial pressure, so it's probably going to be easier for us to do this with moles. The moles of NO should be equal to our total moles minus the moles of N2, because we were given moles of N2. That's this. Okay, so this is our total 6.02887 moles. Remember, this has 3 significant figures, minus N2, which is 6.022 moles. So if we actually subtract those things, we get 0. Oh, that's interesting. Okay, sorry. Getting distracted. 0.0687499 moles. Okay, this is just NO. All right, then where we are now, we did that. We're going to do 3. We're going to get our mole fraction. Our mole fraction of NO is moles of NO. We just figured out 0.006874999 moles divided by the total moles we found earlier, 6.02887. Sorry, moles. I zoned out for half a second there. Notice our moles divided by moles cancels out, so our mole fraction is not going to have a unit with this. Okay, this gives us 0.0011403. Okay, now for significant figure wise, this ends up being 0, which is really stupid. How did this happen? This is 3, 5, 5, 4. So this should be 3, which is 2 decimal places. This is 3 decimal places, so this should be 2 decimal places, which is 1 significant figure. Oh, it's 1 significant figure. That's why. Okay, this is 1 significant figure. So this should be 1 significant figure, which gets rounded to 0.001. There it is. All right. Sorry about that. All righty. This is the kind of stuff we can do with the ideal gas law. All right. We're in the home stretch here. I'll catch you next time. If you have any questions or need me for anything, let me know. I'm here. Okay. Catch you later. Have a good night.